Okay, we're recording. Page 66, number 30. All right, so it wants the limit as x goes to 0 of sine of 2x over x. Okay, so here's what we do know. We know that the limit as x goes to 0 of sine of x over x is equal to 1. That's something you need to know. And here's the deal. As long as what is right here is the same as right here, those numbers can be different. It could be the sine of 2x over 2x. So, oops, that's not the color I wanted. It could be the limit as of the sine of 2x over 2x. As x goes to 0, that'll still give you a 1, or 3x over 3x. Anyway, all of that doesn't matter. So my issue is that this is a 2x and this is an x. And so I need those to be the same in order to use this little rule. You can't change the sign of the angle. You can't change that guy. That one is stuck. It's the same. But algebraically, I can change this denominator x by just doing a little algebraic manipulation. This is equivalent to the limit as x goes to 0 of, what if I did, okay, so I still have to have the sign of 2x. I want 2x down here. So if I'm dividing by 2, which is what's happening with that down there, I can go like 2 over 1 times. It's like I'm multiplying by 2 and dividing by 2 at the same time. And so then that ends up just equaling 2 times, I'm showing more work than you would need to, but this is what's equivalent, 2 times the limit of sine of 2x over 2x. Right? And since these guys now match exactly, this limit is equal to 1, and so it's 2 times 1, which ends up equaling 2. All right. Go over how to find the right and left hand behavior models. Yes. Can you find an example for me? Let's see what left end behavior models was what section. Because most of the time we might ask you to find just the end. Oh, there it is. Okay. We'll have you find an end behavior model, and that's when you just simplify. Whatever it is, and then, but when to ask for a left end or a right end, we usually give it to you, I think. Oh, no. Okay. There's a perfect example. Okay. Here we go. Page. Let's go with page 76, number 45 through 48 are all good ones. Let's find one that has different ones. Let's go with, how about, I don't know, 45? Even 40, I think 46 was one of your homework ones because I think someone asked me about it. It's y equals x squared plus e to the negative x. Okay, so if you remember from before, which you probably didn't, so the graph of y equals x squared would be a parabola opening up, right? And then the graph of e to the negative x is um, an exponential function, but a decay one, right, where it would decrease like this. Okay, and go like that, and these guys go like that. Okay. And then how we would get this entire thing is by adding each of these points together, right? You would take each one. You did this in pre-calc last year where you're like, okay, I think we did it in like the trig section where you'd be like, okay, at 0, I'm going to add these two y values together, and then my new function would be 0 plus 1 is 1. And then at x equals 1, say, you would go and you would take, okay, this is a y value of 1 and this is a y value of 1/9, and so obviously my graph is a little wrong, but you would be something like this, and then over here. Anyway, so you end up, for each x value, you would add up the two y values, and so this graph would be big like that. And anyway, so that's what this is happening. You're taking these two functions, you're adding them together, and at each x value, you would be adding the y values together. And so what happens is, as you're like zooming way out and getting further and further out towards either positive infinity or negative infinity, you're adding these y values together, and one function overpowers the other. One function definitely has bigger y values than the other function. And so let's look at the right-hand side. Is much easier to see right now. Obviously, this e to the negative x, as you're going to infinity, the y values are so small, and you're adding them to this x squared function that you're basically end up almost adding 0 the further along you get over here. Like, let's say when x is 10, you've got 100. So like when x is 10, and obviously we're going to go much bigger than that, then your y would be like 100 plus e to the negative 10, which is such a very small number. It's, that's 1 over e to the 10th. So 1 over 3-ish to the 10th power. And so it ends up just being basically 100. And so the x squared function is way bigger in y values than the e to the negative x. And so the right end behavior would be x squared. The left one, we're going to study this more this year, but an exponential function is going to grow much faster than a squared function, right? So if you look at, I don't know, let's go with negative 10. Just, okay, so you would have 100 again, because negative 10 squared is 100, but then you're going to be adding e to the negative 10, so it'll be a positive 10. So that's like 3 to the 10th power, which is huge, plus 100. Well, that huge number is like growing way faster than the 100 is. And even as you go even further, it's even more. So your left end behavior is going to be y equals e to the negative x. And then you will need to prove that, right? Okay, so those are your two guys. To prove the right-hand side, you would take the limit as x goes to positive infinity. So this is for the right side. For right, you do positive infinity, and you'll put the original function, x squared plus e to the negative x, over the function you're saying is the right end behavior, so over x squared. And then you'll do some algebraic manipulation, and this is the limit as x goes to infinity. You must write this every time. Don't leave off the limit as x goes to infinity, because otherwise it's wrong. Plus e to the negative x over x squared, which e to the negative x is the same thing as dividing by e to the x. And so as x goes to infinity of 1 plus, this would be like 1 over x squared e to the positive x now. And when you plug an infinity into that, you're basically dividing by infinity. It'll be like a 1 divided by infinity. So this zeroes out right there. And then now you've got, okay, the limit as x goes to infinity of 1 is just 1. And that's what you're proving. You're proving, to prove that this is true, you need your limit as x goes to infinity equal 1. Left-hand side, you want the limit as x goes to negative infinity, since we're doing the left. You're going to put the original function, the x squared plus e to the negative x up top. You're going to divide by the function that you're saying is the left end behavior, which we said was e to the negative x. And then we can split that up, and that would be the limit as x goes to negative infinity. That would be an x squared over e to the negative x plus e to the negative x over e to the negative x, which is 1. And then do you see, like if you plug in a negative infinity into x and then you square it, that would be a positive, right? But e to the negative infinity would be a positive e to the positive infinity down below. So you're dividing by infinity, which definitely zeroes out much faster than an x squared. And so this is equal to 1. And that's what you needed to prove, that when you divide it, then it's that it is equal to 1. All right, hopefully that makes sense for the end behavior models. Okay. I need you guys to not type any more, don't add more questions until we get through the ones that are listed right now. Otherwise, I'm just going to lose my spot on here. Okay, number 10 from the quiz is next. 10 from the quiz. Of course, I grabbed a pencil that doesn't work. 10 quiz, 10 review, multiple choice. 11 review worksheet. Okay, and then instant. Okay, so I'll go back to it. Okay, number 10 from the quiz is the exact same thing that we just did. Okay, here's quiz number 10. We actually tell you that the right end behavior model. All right, so here's the original function, and we are saying that the right end behavior model is y equals x. And so, and we say use limits to prove this is true. So you need the limit. If we're doing the right-hand side, you go as x goes to infinity of your original function over x, and then you're going to simplify this, write the limit as x goes to infinity. You will lose points if you're not writing the limit as x goes to infinity on every step. If it's the left-hand side, then it's as x goes to negative infinity of 1 plus the natural log of absolute value of x over x. And then so I don't know, hopefully you guys, if you don't remember, natural log of x looks like this. And then when you're, so as you go to infinity, it is getting bigger, but it's pretty small as you're going to infinity. But it does end up getting larger and larger there, just a very slow growing one. And then, but we're dividing by infinity, and so it ends up, that guy zeroes out. This guy zeroes out because you're dividing by something much larger, like it's going to infinity versus the top is getting there but way slow, and so it's equal to 1. Boom, done. If it was a left end with the only thing that would be different, yes. The only thing that would be different is if it is a left end behavior model, you're going to be taking the limit as x goes to negative infinity each time. And then just keep in mind that, so keep in mind that if you have a, like on that last example, I thought that was really great, an e to the negative x. When you plug a negative infinity into e to the negative x, well then that's like saying 1 over e to the negative of negative infinity, which means it's a 1 over e to the positive infinity, which means that it's going to zero out, right? 1 divided by infinity, maybe I should have written it like that. It's like 1 over infinity, and 1 over infinity is 0. So that if you get something of 1 over 0, you're going to say that, call that infinity, and if you have 1 over infinity, you're going to call it 0. Just a side note, that's what happens with those guys. So yeah, so be careful with that, right? Depends on if you had a e to the x, but as x goes to negative infinity, well, that's going to be like an e to the negative infinity, which is like a 1 over e to the positive infinity, which is like a 1 over infinity, which is 0, versus the limit as x goes to positive infinity of just e to the x, that's like e to the infinity, which is 3, almost 3, to the infinity power, which ends up being infinity. So just be careful with those negatives and when they're in the bottom versus the top. And negative exponent tells you to take the reciprocal, right? So, okay. Next question was chapter 10, review multiple choice. Instantaneous rate of change. Okay. So instantaneous rate of change is the slope of the tangent line at that point. And so that means you're going to be doing the limit as h goes to 0 of f of x plus h minus f of x all over h. You're taking the limit as h goes to 0 of the difference quotient, and then whatever your, like this x is going to be that point, like that point, or that t value, or what is the problem on this thing. So that's how you're going to find instantaneous rate of change. It is the slope of the tangent line right at that point. So this problem, and I'm going to need to go to the next slide because otherwise I will definitely run out of room, but let's just try it. Okay, this problem was f of t is t plus 2 over t, and they want it at t equals 2. Okay, so keep in mind that f of t plus h, I'm going to just show you separately on this, would be a t plus h plus 2 all over the t plus h. So careful with that. T plus h, right? Because that's your function. And then f of t would be this whole thing. I think most of you did it this way. You also can plug in the 2 into the t right away. Okay, I'm going to go to the next slide though. All right, so I'm going to do the limit as h goes to 0 of f of, I'm plugging the 2 into the t, plus h, minus f of 2 all over h. That's going to be what I'm finding, right? And, you know, limits, you want to plug that value in, right? Well, if you try to plug in a 0 into h right now, you're going to be dividing by 0. Not okay. So we got to do some algebraic manipulation here. All right, so this is equal to, make sure you write the limit as h goes to 0 on every step. If it says show your work or whatever, which it will, yeah, by the definition, it will have you do it. Okay, so f of 2 plus h is 2 plus h plus 2, so that was your t plus h, right? All over 2 plus h minus f of 2 would be, I'll write it, 2 plus 2 all over 2. And this is all over h. Let me just do that just so you see it's a fraction within a fraction. Did I do that right? Plugged in a 2 plus h into t on the top, on bottom, minus f of 2 is 2 plus 2 divided by 2. Okay, got it. All right, so then this is the limit as h goes to 0. Your goal is to end up getting that h that's in the bottom to go away. All right, so that ends up being what? 4 plus h all over 2 plus h minus 4 divided by 2 is 2. Still all over h. To subtract these fractions on the top, you need a common denominator. So I'm going to write it like 2 over 1, and then I'm going to multiply top and bottom of this fraction by 2 plus h, so that then I can subtract. All right, so this becomes the limit as h goes to 0 of, it'll be a 4 plus h minus a 4 minus a 2h all over 2 plus h, and then all over h, because it's a, whatever, that makes sense. All right, and then simplifying that, this 4 will cancel with that 4, yay, and then we have an h minus 2h, so that means I've got the limit as h goes to 0 of a negative h over 2 plus h all over h. I'll rewrite this just so that it's more obvious that the h's are going to cancel. The h in the denominator better cancel with completely, or else you've done something wrong. But dividing by h is the same thing as multiplying by 1 over h. So I write it like that, so that way it's more obvious that the h's have canceled. And so you are left with the limit as h goes to 0 of a negative 1 over 2 plus h. Plugging in that 0 into h now. Now you can plug it in because now you won't be dividing by 0 when you do. And so your answer should be negative 1/2. Yep. Negative 1/2. All right. Someone said 11 on the chapter 2 review. Can you please explain aim behavior models when it's either positive or negative fitting, like number 11 on the worksheet chapter 2 review? Worksheet chapter 2 review. Oh, okay. Yep, got it. Okay. All right. So here's also the worksheet number 11, and it's the limit as x goes to negative infinity of 3x cubed plus 2x squared over x minus 7x squared. All right. Okay. So probably the best way, I mean, the way we did it last year, and I'm sure you guys remember the month of May last year, right, as you were getting out, right, in pre-calc? Not really. You can think about it that way. What we did last year was we divided top and bottom by the highest degree exponent on the bottom. So I would divide by x squared. So here's one way to do it. Divide by x squared, every single term. And what you end up with is a 3x cubed divided by x squared would leave you with a 3x. And then a 2x squared divided by x squared would leave you with a 2. And then the bottom, we would have a 1 over x and minus 7. Yeah. And then, so that what would end up happening is when you plug in an infinity into this x, 1 over x, well, into the x of 1 over x, this guy will end up zeroing out because anything divided by infinity, and then you got that minus 7. And so when you plug in that infinity, you're going to get both positive and negative, yeah. So you're going to end up having a 0 minus 7, right? So a negative number down below, and up top you'd be having a 3 times negative infinity. So this is like a negative infinity divided by some negative 7, I guess, right? The 7 doesn't really matter, and so that ends up giving you a positive infinity, which was the answer. Hopefully that makes sense. That was the last one I wrote. Let me scroll up and see what other questions you guys have. Okay. Okay, instantaneous rate problem. I did. Yay. Page 9629. Do an example of an AP multiple choice question for both an. Okay, I'll try on that. Multiple choice AP. There was one on the quiz. Can you do number 9? Multiple choice worksheet. 7. If it was a left one, okay, I answered that. Okay, cool. All right, I've got everything written down now, so I mean, don't go hog wild on filling up that chat screen with more questions, but you can definitely type in more. Okay, so we are on page 96, number 29. Piecewise function. Okay. All right, page 96, number 29. Okay, let's see if I can draw this. Nope, that's not what I want. What did I want? I want this. Bump. What am I going for? -1, -1 to 0, 0, 0. Okay, perfect. And we'll go. Okay. Go back to pen. Okay. So it says for x is 1, okay, we'll go 1 and 1 and 1, let's say. Okay, so it says your y value is 1 for x is less than or equal to 0, so it's like that. And then it's a negative x from between -1, so it'll be a +1 to 0. So negative x, and these are both open. So open, when x is -1, it'd be a +1, so it's an open there, but then it ends up connecting like that. When x is 0, y is 1. From 0 to 1, it's a negative x. So 0 to when x is 1 would be a negative 1. Open, toot, and then 1, and there we go. Okay. Type right if you guys, hopefully I drew that right. I don't have the answer key with me, so hopefully that's right. If you see a glaring error on how I just graphed that, let me know, because I'm going to be basing all my answers off of what I just graphed. Find the right hand and left hand limits of f at x equals negatives 1, 0, and 1. Okay. So the limit, so this is A, the limit as x approaches -1, and then they want right and left hand limits. So let's go with from the left. We're going to call this f of x. Okay. So the limit as x approaches -1, but from the left, that means you're on this right here, and your y value is positive 1. So that's a 1. The limit as x approaches -1, but from the right, you would be traveling along this guy, but its y value is still going to 1, so it's also a 1. And then, and so we would say that the limit exists at x as x approaches -1. So part B, does the limit exist? So because of these two guys equaling each other, then the limit exists. So the limit as x approaches -1 of f of x is 1. That's what we say, because the left-hand side and the right-hand side match, and so the limit exists. At 0, it's going to be the same thing. The limit as x approaches 0 from the left is going to equal your y value. So from the left, you're going this way, your y value is 0. And then also from the right, you're on this guy, you're heading there, your y value is also 0. So the limit as x approaches, sorry, this is messy, I should have given myself more room, it's also 0. And so the limit, because the left and the right-hand side limits exist, or match, then we say that the limit as x approaches just 0 is equal to 0. It exists and it's equal to 0. Here's the one that's more interesting. They wanted 1, right? Yeah. Okay, the one that's more interesting is, I'm going to come up here. The limit as x approaches +1 from the left, it means that I would be, here's +1, right? Here's where x is 1. You would be on this guy if you're coming from the left, and your y value is -1. And then the limit as x approaches +1, but from the right. So here's +1, your x is 1. You're coming from the right, so that means you're on this line, this right. Your y value is 1. And so here we say the limit does not exist. So the limit as x approaches just 1 of f of x does not exist, and it's because the right-hand side, these guys are not equal. The right-hand limit and the left-hand limit don't match, and so the limit just as x approaches 1 does not exist. So that was part A and part B that I answered as I did that. And then they want to know, is it continuous? So to be continuous, you need the, what do they want it at? They want all 3. Okay. So to be continuous, there's 3 parts of the continuity definition. You need your function to exist at that point, the function's value, right? So you need to be able to say, at x equals -1, your y value is this, for sure. There's a closed dot there, right? And at x equals 0, you need an actual like y value there. And in each of these points, at -1, we've got my y value is 1, and at 0, when x is 0, your y value is 1, and when x is 1, your y value is actually 1. So the function exists, right? It's defined at all three of these points, so it satisfies that part of the definition. The second part is that the limit needs to exist for it to be continuous. And so at x equals -1, we said the limit existed. The limit was equal to 1, right? Because the left-hand side and the right-hand side limits matched, and so the limit exists. And then at 0, we also said the limit exists because from the left and from the right hand side limits, they matched, and so the limit exists. It was equal to 0. At x equals 1, though, we said the limit did not exist, right? Here, the left-hand and right-hand side limits didn't exist. So right away, it fails part 2 of the definition of continuity. And so it's not continuous at x equals 1 because the limit does not exist at x equals 1. And then the third part of the continuity definition is that that function's value must match the limit, right? So at x equals -1, your limit exists, right? So we're good on that. And then f at -1, what is the function's value at -1? We said it was 1, and the limit as x approaches -1 is also equal to 1. And since these two guys are equal, then we say that it is continuous at x equals -1. So at x equals -1, it is continuous because limit exists and it is equal to the function's value. I'm running out of room, so I have to go to the next slide to show you the other two. Oh, do not restart me right now. Remind me tomorrow. Oh my goodness. Wanted to restart my computer in the middle of this. Okay. I'm going to go to the next slide so that I can write the notation, but we already know that because of this guy that at +1, it's not going to be continuous, right? I'll write that on the next slide what to say, but that's because the limit just doesn't even exist, right? And then here's where it gets interesting, is that your limit exists, right? We said the limit existed at x equals 0, but the problem is that your function's value is not equal to that limit, and so that is not going to be continuous. So it's continuous here at -1, but it is not continuous at 0, and it is not continuous here where you've got this big old jump going on there. So okay, so to be continuous, you need f, I'll use c. F of c is equal to some number, right? It means that the function is defined there. And then you need the limit as x approaches c, that whatever that value is, of f of x. The limit exists. And for the limit to exist, that means that left and right limits are equal. And then, so that's part 1. Part 2, the third part is f of c needs to equal the limit as x approaches c. So c is going to be some number, right? In this last case, it was -1, 0, and then 1 for each of the cases. Sorry, we already talked about the limit, that it's continuous at -1. We're going to say for 0, what the frick happened with 0? With 0, we said, hold on, let me go back. What was 0? The limit existed. Come on. Don't be slow on me. Okay, the limit was equal to 0, but f of 0 was 1. Okay, so for So at x equals 0, f of 0 was 1, and the limit as x approached 0 was equal to 0, and since these two guys are not equal, then we say it's not continuous. And then at x equals 1, it was the limit, the limit as x approached 1 of f of x did not exist, and so that means not continuous. When is a function continuous and not discontinuous again? Hopefully you typed that before I just wrote this and I didn't see it. But okay, good. Yes. All right. So then I'm glad I wrote that. So it's got to satisfy those three pieces, right? For it to happen. Okay. So that was that one. Number 9, multiple choice. Okay. I'm going to skip number 9 just because it's a cubic and you won't need to do a cubic. It's complicated. I did number 10, which it's the same process to do number 9. It's just, it's a cubic, and so then you have to do the whole t plus h quantity cubed, and it's a pain in the butt. So, and it's just a lot of work. If it was a squared, by all means, that would be something you definitely would want to do. Okay, number 7, equation of the tangent line. Okay, perfect. Here's a squared. So here's the multiple choice review worksheet number 7. They're asking you to find the equation of the tangent line. Could easily ask you instantaneous rate of change also on this question. It's asking the same thing for slope, right? So the slope you find the same way. So x squared minus x, and this is at x equals -4. Okay, so to get the equation of the tangent line, you need a slope and a point. And then the slope, m, is found by doing the limit as h goes to 0 of f of x plus h minus f of x all over h. That's how you find the slope of tangent line. Or instantaneous rate of change, same thing. Okay, so that means this will be the limit as h goes to 0 of, it's a x plus h quantity squared minus x plus h minus x squared minus x. You had lots of practice with the difference quotient last year, all because of this. Because it's not hard, it's just, yeah. It was when x is -4. We could plug that in right now, or we could plug it in at the end. Let's just plug it in at the end. Why not? I think I did the last one where I plugged it in at the beginning. It works either way. So this is an x squared plus 2hx plus h squared minus an x minus h minus x squared and a plus x all over h, because I distributed this minus sign to both and I distributed this minus sign to both. Now, hopefully you were told last year, I know I told my students, hopefully you remember, at this point, anything without an h in it had better cancel. And if it doesn't, you did something wrong, because the h in the bottom better cancel. So that way we can plug 0 into it. Those x's cancel. So all I have left now have h's in there. So yay. So this is the limit as h goes to 0 of, I'm going to factor out an h. I would be left with a 2x plus h minus 1. Don't forget this. There's an h right here. When you factor out the h, there's a 1 left. That's all over h. Cancel those out. Now you can plug in the 0 into h, and so you've got a 2x minus 1, and when you evaluate that at x equals negative 4, so if I plug in negative 4 here, so at negative 4 you would have 2 times negative 4 minus 1, which is negative 9. Yeah, so that's your slope of the tangent line. So that's your slope. And I have to go to a new page. But because we want the equation of the tangent line. So you got that slope is negative 9. And I wish these slides were just a teeny bit bigger. If I could just slide them up. Oh, that would be wonderful if I could just roll them up instead of having to go to a completely new page. I'll have to ask if that's possible. That would be awesome. Okay, so we had the y equals x squared minus x was our original. We want at x equals negative 4. We just found that your slope is negative 9, right? We just found that. And then, so that's your slope of the tangent line, and then a point on the tangent line would be negative 4 for x, and then you're going to plug in the negative 4 into your function to figure out what the y value would be, which would be, what, 16 plus 4, which is 20. Okay, so there's your point. Plug it into point slope form, which is y minus y1 equals m times x minus x1. So you got a y minus 20 equals negative 9 times x minus negative 4. Okay, so if it's a free response question, like you're putting your answer on the blank, there's where you're going to leave it. This was multiple choice. This is when you do need to do the practicing of simplifying this into another form. So negative 36, but plus 20 would be a minus 16, I believe. Oh, yes, it is. Okay, there you go. If it's not multiple choice, then by all means, leave your answer this way. Leave your answer in point slope form, but if it's multiple choice and you got to match, then you got to match it. All right, so that was number 7. Okay, got that. Can you please find and prove an end behavior model? I did that already. Page 66, number 33. Okay. Page 66, number 33. A lot of this is algebraic manipulation, which is why schools require you to take so much algebra before you get here, because it's this algebraic manipulation that you have to do. You become master manipulators between the end of everything. All right, so keep in mind, you are going to use that the limit as x goes to 0 of sine of x over x is equal to 1. You got to know that, right? So I'm going to rewrite this as sine of x times sine of x over x. That's what sine squared is, so it's like sine of x over 1 times that. Sine squared is sine times sine, and so that's equivalent. And then this is equivalent to, you do not need to show me this work, but it is true that this is equal to the limit of, as x goes to 0 of sine of x times the limit as x goes to 0 of sine of x over x. And this guy is 1 times this guy. Better know your trig functions and the values, right? Sine of 0 is 0. And so that's how your answer becomes 0. Yes, okay. That was number 33. How to sketch a function like number 1 on the quiz. Okay. Because, yeah, there's going to be one like number 1 on the quiz, but it's going to be even more, we'll have more rules for you, I'm sure. Okay. So, quiz number 1. What you want to do is just make sure that each part is satisfied. So it says sketch a function. So make sure that whatever you draw passes the vertical line test. Which means every time you draw a vertical line, it should only go through the graph once. So doing something like, I'm trying to think what you guys do where you mess it up. Like you'll have something and it'll be like, oh yeah, the limit is going to here. And then, oh yeah, the limit over here is going to here. No longer a function and you don't get full credit, right? You may be correct in that as x goes to negative infinity, your y value is 0 or something like that, right? And as x, whatever, I don't know. Giving you gibberish stuff right now. But anyway, watch out. Like, be careful before your final answer that if it's saying a function, which more than likely it will, because, you know, that's what we like to do. Make sure it's actually a function, that it'll pass the vertical line test. Okay, it says a removable discontinuity at x equals -2. That means there better be an open dot there. Right? An open dot or a hole at x equals -2. It also means that your graph should keep on going. If that makes sense. Like it should be like something like that, right? You don't, it's not just an open dot and then only continuing on one side for it to be a removable discontinuity. It's kind of like, oh, you have this straight line with an open dot right smack dab in the middle of the graph. An infinite discontinuity at x equals 1 means that you should have a vertical asymptote, which means your graph does not cross it, right? You shall not cross that vertical asymptote. And your graph should not touch that either. You don't touch that asymptote at all. And then a jump discontinuity at x equals 2. So a jump discontinuity should be something like, you've got two different y values coming from opposite ends. So like something like this. I don't know. It's it doesn't have to be exactly like that. One of them might be curving or whatever, but some kind of jumped there. And then that's all it said. So here's what I drew. This is not the only correct answer. I did, I started with the asymptote because I didn't want to cross over that. So at x equals 1, I drew a vertical asymptote, right? And then I kept in mind, okay, I need to make sure that, you know, at a vertical asymptote, you should have, you know, I'm going to erase this after I write it, but you should have either going up like this and getting close, or it should be coming up like this and, come on, getting close but not touching, or like this, or like this, right? Not, it doesn't need to be all of those, and in fact, if it was all of those, you'd be wrong because it's no longer a function. But a vertical asymptote, your graph should be coming up real close, but not actually touching them. So I know I need to draw some kind of thing like that. And okay, so I do that. And then a removable discontinuity at -2. Okay, well, here's -2. I happen to draw it right here. You didn't have to. And in fact, I went, oh, there's nothing else. You know, the other point I need to put is over here at +2. So I went, all right, well, I could actually make that like okay, it's going to be going up like that. And then I continue it along like that. Again, not the only thing you had to do. And then at 2, we have a jump. And so I made it where I did an open dot with it going up like this. And then a closed dot and go in like this. It's a function. If you draw a vertical line, it's only passing through the graph one time for each x value. And it satisfies all of the conditions. So that was what I did. You could do more different. There were lots of correct answers, and we literally just go and I go, okay, function, yep. Is it did they show a removable discontinuity there? Yep. Did they do an infinite discontinuity there? Yep. Jump, yep. Good. Credit, you know. So there will be, this was only 4 conditions. I'm pretty sure if I remember right, there's a lot more conditions we have you satisfy, but just do that. Number 3 on the quiz. Okay, good one. So we can talk about continuity again, because it says using the definition of continuity, explain using math notation why or why not this guy is continuous. So we've got a piecewise function, and that guy. All right, so at x equals 2, if we don't give you, I don't remember if we give you the value. In this case, we did say at x equals 2. We didn't have to say that to you. Like, you would know where to check for continuity. You know, here, look, you've got 2 different values when x is 2. Well, you've got 2 different rules for your y value at x equals 2. And so if there is a discontinuity, it's going to happen at that spot. So that's where you look for it. If we do, I think we give it to you, but anyway. Okay, so for continuity, you need, first of all, that f of 2 is defined. Okay, so remember the or equal to, so that means f of 2 is going to equal 3 times 2, which is 6. So f of 2 is 6 here. And so it is defined. Check. You got satisfies part 1 of the definition. Part 2 is that the limit exists. And so for the limit to exist, you need to check the limit as x approaches 2 from the left. From the left of f of x. Okay, so from the left, here's x is less than 2. That's from the left. Because it's all the x values left of 2. That means that it would equal 2 squared plus 2, which is 4 plus 2, which is 6. So the limit as x approaches 2 from the left is 6. The limit as x approaches 2 from the right, this is for x greater than or equal to 2, so this is from the right. You're going to plug it in that way. I'll graph this for you in just a second to show you that what I'm saying to you is true. Like that works. Okay, so from the left is 6, from the right is 6, and so since these two guys are equal, then we say the limit as x approaches 2, not from the left or from the right, just 2, is 6, because from the left is 6 and from the right is 6. And then part 3 of the continuity definition says since the limit as x approaches 2 of f of x is equal to 6, which is equal to f of 2 as well, then f of x is continuous at x equals 2. And then this graph, I just noticed that my chat box was scrolled up. Shoot. Hopefully you guys okay. The graph of this would be this. X squared plus 2, you got, so this would be like an open, it would have been like this. Nope, wrong way. Pooper scooper duper. Pretend like that didn't just happen. Okay, when x is x squared, okay, x squared plus 2 would be a opening parabola opening up like this, like that, but with an open dot there, and then x is greater than or equal to 2 would be a straight line, slope of 3, and so, and it's a closed dot, and then it would be like that. Okay, so there's your graph, right? So it definitely fits that it's continuous. And then from the left, you're on this guy heading towards x equals 2, and your y value is 6. From the right, you're heading this way, but your y value is still 6, and so it is continuous. What's the difference between the equation of the tangent line and the equation of the normal line? That's a good question. Okay. Equation of tangent line versus normal line. The only difference is the slope. Slope of tangent line is the whole limit as h goes to 0 of the difference quotient, right? And then slope of the normal line will be opposite reciprocal slope from tangent line. So if we find that the tangent line, well, that last one, right? The last one I did when I found the equation of the tangent line, the slope was -9, I think. And so then the normal line will be, the slope is a +1/9. And so I don't remember the exact points, but it was like, I don't know, y minus 20 equals -9 times x plus 4. This guy will be y minus 20, same point, right? Because we're still talking about the same x value, 1/9 times x plus 4. There's your difference between equation of the normal versus equation of the tangent. Okay, what time are we at? We're at 8:03, and I think I started on time. Let me just look at 19 and 14 on here and just make sure, are they do or die? 19 is determine it algebraically. Yep, you need to know that one. And power function, find a power function in behavior model. Okay, that one's easy too. Okay, I'll answer these last two, but then that's it. Number 19 on the worksheet. 14 is super fast. Number 19 is finding this guy algebraically. The limit as x goes to 5 of x squared plus 4x minus 45 all over x squared minus 25. Okay, so your first thing is when they ask you to find the limit, try plugging that value in. And the problem is, so if you can plug it in and you get values, you're golden, that's your answer, right? If you try to plug that in right now, you plug a 5, the top looks like it'll be okay. Oh no, it won't, will it? 25 plus 20. So no, you end up with a 0/0 if you just go straight up plugging it in right now. So you can't. You're going to do some algebraic manipulation. We need to get it to the point where we're not dividing by 0. Factor the top and factor the bottom. What would that be? A +9 and a -5, I believe. Looks like it to me. And then x squared minus 25 is the difference of two squares, so an x plus 5 and an x minus 5. Those guys cancel. Now you can plug a 5 in and not be dividing by 0, right? So this is equal to a 5 plus 9 over 5 plus 5, which is a 14 over 10, which definitely reduces to 7/2, which, did I make a mistake? Yeah, I made a mistake. 7/5, not 7/2. 10 divided by 2 is 5. There you go. So that's 19. So yeah, factor, simplify, and I'll get you there. Number 14, find a power function end behavior model. Listen, when it's a polynomial like this, you're just going to take the largest exponent with its coefficient. Your end behavior is y equals 4x squared. I could prove that by dividing it on both sides, left and right, and all of that. And anyway, think about it this way. It's just like as you zoom out, the 4x squared ends up being the most powerful part of the whole guy. 4x squared, compare that to 4x, compare that to 9. This 4x squared is absolutely going to give you the biggest, either plus or minus, I don't care about the sign. It's going to give you the largest in the absolute value of the y values of each of the pieces of this guy. And so that's going to be, anytime it's a polynomial, it's just that. Okay, that's it. Good luck. See you tomorrow. You'll be fine.